Hello learners, welcome to Sure Question Academy. Please watch the videos, like and subscribe to the channel.
Welcome back. Let's tackle a classic ray optics problem that tests our understanding of lenses. Here is the scenario. An object, 6 centimeters tall, is placed 60 centimeters in front of a lens. A clear image is caught on a screen that is 40 centimeters away on the other side. Now here is the twist. If we take that exact same object and move it closer, so it's only 40 centimeters away from the lens, what will be the new height of the image? Take a second to visualize that. To crack this, we need to treat the problem like a puzzle with two cases. Case 1 will give us a hidden clue about the lens itself, which we will then use to solve case 2. Let's dive into case 1. Our first job is to extract the given data. To get full marks, we must strictly apply the new Cartesian sign convention. Let's do this carefully. First, the object height, HO. Since we always place objects upright above the principal axis, our height is positive 6 centimeters. Next is the object distance, U. According to our sign convention, the object is placed to the left of the lens. Anything measured to the left is negative, so U is minus 60 centimeters. Now for the image distance, V. The question mentions the image is formed on a screen. This is a massive hint. Only real images can be caught on a screen. And since real images are formed on the right side of a convex lens, we must be positive. So, V equals plus 40 centimeters. So, what's our hidden clue? It's the focal length, f. We don't know the power or the focal length of this lens yet. Let's calculate it. We start with our standard lens formula. 1 by f equals 1 by v minus 1 by u. Always write the primary formula first, as it carries step marks. To make calculation easier and avoid messy fractions later, let's take the common denominator. 1 by f becomes u minus v, all divided by u times v. Now, just take the reciprocal of both sides to get f directly. The focal length f equals u times v divided by u minus v. This little rearrangement is a great time saver in exams. Let's plug in our values. Keep those negative signs safe. We have minus 60 multiplied by 40 in the numerator divided by minus 60 minus 40 in the denominator. Multiplying the top gives us minus 2400. Adding the bottom gives us minus 100. The negative signs cancel out, giving us a focal length of exactly plus 24 centimeters. That positive sign mathematically proves we are dealing with a convex lens. Clue number 1 is secured. Fantastic. Now let's move to case 2. We are taking the object and shifting it closer to the lens. Our new object distance, let's call it U2, is now 40 centimeters. With the sign convention, it's minus 40 centimeters. But remember, it is the exact same lens. We haven't changed the glass. Therefore, the focal length f remains plus 24 centimeters. See how case 1 just unlocked case 2 for us? Our next milestone is finding exactly where the new image forms. We need to calculate the new image distance, V2. We start by writing the lens formula again, tailored for case 2. 1 by V2 minus 1 by U2 equals 1 by f. We want V2, so let's keep it on the left. Shifting the other term gives us 1 by V2 equals 1 by f plus 1 by U2. Just like before, let's cross-multiply to get a single fraction. 1 by V2 equals U2 plus F divided by F times U2. Take the reciprocal. Our rearranged formula is V2 equals F times U2 divided by U2 plus F. Now, let's carefully substitute our numbers. 24 multiplied by minus 40 divided by minus 40 plus 24. The numerator becomes minus 960 and the denominator simplifies to minus 16. Dividing these gives a nice, clean, positive 60 centimeters. So, our new image is formed 60 centimeters to the right of the lens. We are almost at the finish line. To find the final height, we first need to understand how much the lens magnified the object. Let's calculate the magnification M. The formula for lens magnification is V divided by U. In this case, V2 divided by U2. Plugging in our distances, that is 60 divided by minus 40. The zeros cancel and 6 divided by minus 4 gives us a magnification of minus 1.5. This tells us the image is 1.5 times larger. Now for the final answer. Let's calculate the height of this new image, hi. We know magnification is also the ratio of image height to object height. So, M equals hi divided by ho. Rearranging that, the image height hi equals magnification M multiplied by the object height ho. Substitute our magnification, minus 1.5, and multiply it by our original object height, which was 6 centimeters. And we get minus 9 centimeters. In physics, that negative sign is a story in itself. It confirms that the final image is formed below the principal axis. It is a real, inverted image. Always write down this final interpretation to secure your full marks. And there you have it. By breaking it down into two cases and following the sign rules, we solved a complex problem easily. Keep practicing, and I'll see you in the next lesson. Happy learning!